welcome to today's deep dive. I mean, what if the secret to making a massive, multi-billion parameter AI smarter wasn't, just building a bigger supercomputer? What if it was just pairing it with a tiny, relentless critic?
Yeah, it completely upends that whole bigger is always better narrative we've seen dominating the tech industry for, well, the last half decade, really.
Right. We've been so focused on sheer scale that we've kind of ignored the power of specialized architecture. And the scale we're talking about is almost incomprehensible.
Oh, absolutely.
Like if a massive AI makes a mistake today, say it writes a faulty SQL query or hallucinates some code, the traditional instinct is to gather a mountain of new data and retrain the entire system.
Which means gigantic server farms grinding away for months.
Exactly, burning astronomical amounts of money and energy just to fix a cognitive blind spot. But our mission for this deep dive is to explore a radically different approach. We're looking at the AutoResearch 2.0 framework and this fascinating concept called self-evolution.
Yeah, it's all about how we can make these massive systems dramatically smarter without ever touching their underlying code again.
So let's get into it. To understand how AutoResearch 2.0 pulls this off, we really have to look at its foundation, right?
Right. The whole thing is built on this concept called dual agent asymmetry. So instead of relying on one monolithic brain to do everything, the system creates this highly asymmetrical relationship between two totally different AI agents.
Let's break those down so we can see how they interact. On one side, we have Agent A, the action policy model.
Yeah, that's your classic, massive, cloud-based giant. Think of a model on the scale of Gemini 3.1, boasting something like 32 billion parameters.
Right, and its entire role in life is just task execution, right? Direct environment interaction.
Exactly. If you need a database queried or a complex physics problem solved, Agent A does the heavy lifting. But here's the critical part. Its weights are permanently frozen.
Okay, wait, let me jump in there. Frozen weights is a term that gets thrown around a lot. What does that physically mean for the model?
It basically means the billions of mathematical connections inside that giant neural network are locked in a vault. There are no gradient updates, no retraining, no structural changes at all.
So the massive model you deploy on day one is the exact same model you have on day 100.
Yep, which saves you an absolute fortune in computing costs.
Right. But that brings us to the other side of the asymmetry, Agent B, the self-evolving policy model.
Right, and where Agent A is this massive cloud-based thing, Agent B is tiny, and it's local.
Like a compact model, maybe a Quinn 4 billion or 8 billion parameter setup.
Exactly, and it does not execute the primary tasks. Its entire role is pure meta-reasoning and hypothesis generation.
So it just observes the giant, diagnoses its failures, and then rewrites the context instructions to steer the giant back on track.
Precisely. And crucially, unlike that frozen giant, this tiny model is in a state of active reinforcement learning.
Oh, so it's constantly adapting based on real-world feedback. Okay, let's unpack this. So instead of trying to make one giant brain do absolutely everything, it's like having a massive, incredibly strong construction worker taking very specific, localized instructions from a tiny, brilliant architect.
The roles are right, but let's take that analogy a step further to capture the mechanism. It's actually closer to a massive factory floor of heavy robotic assembly arms.
Okay.
And the tiny model is a single, highly specialized quality control inspector sitting in a booth above the floor.
Oh, I see. So the inspector isn't strong enough to lift the car parts, but they're constantly watching the arms.
Right. When an arm drops a bolt, the inspector doesn't try to go down and rebuild the arm's motor. They just rewrite the assembly manual being fed to the arm on the fly.
Like saying, grip 3 millimeters to the left next time.
Exactly. That's the asymmetry in action.
I'm stuck on something here, though. I mean, if a 32 billion parameter giant is smart enough to write complex software, why is it too dumb to spot its own typo?
That is the big question, yeah.
Doesn't the big brain have enough processing power to just look at its own output and realize it dropped the bolt? Why do we even need the tiny inspector?
To answer that, we really have to dive into what researchers call the cognitive separation principle. And to grasp why this specific separation of duties is so vital, we actually need to look at physics.
Wait, physics?
Yeah, specifically how physicists handle overwhelmingly complex systems. There's this concept called the Born-Oppenheimer approximation.
Okay, taking us into quantum mechanics here. How on earth does particle physics translate to AI prompting?
Well, in physics, if you want to calculate the behavior of a molecule, you hit a massive mathematical wall. You have these incredibly light, fast-moving electrons buzzing around, heavy, slow-moving atomic nuclei.
Right, they operate on completely different scales of mass and speed.
Exactly. So trying to compute their movements together in one tangled mathematical equation is basically impossible. So the Born-Oppenheimer approximation separates them.
Meaning, physicists calculate the electrons while assuming the heavy nuclei are perfectly frozen in place.
You got it. It isolates the variables to make the math actually solvable.
And AutoResearch 2.0 does the exact same thing for cognitive loads.
Precisely. It separates the incredible complexity of direct task execution, the heavy lifting of the large model, from the pure abstract logic of meta-reasoning done by the tiny model.
Right, because diagnosing a batch of failed SQL queries requires an entirely different cognitive pathway than the act of generating the action in the first place.
Exactly. Identifying the underlying logical flaw and formulating a linguistic rule to prevent it. That is a fundamentally different task than predicting the next token in a line of code.
So by dedicating an entire parameter space exclusively to textual optimization, the tiny meta model gets incredibly efficient at that one specific job.
Yeah, what's fascinating here is there's a massive secondary benefit to that separation. The tiny model doesn't even need to know how the massive model's brain is wired.
Wait, really? It doesn't care if it's Gemini or something else, it just focuses purely on perfecting the text going in.
Not at all. It treats the giant model like a total black box.
Yep.
That agnostic relationship is where the true flexibility of the framework lies.
Wow, so it just observes causality. Like, when I feed it instruction X, it produces output Y.
Right. And when Y is a failure, how do I change the wording of X? You aren't tethering your diagnostic intelligence to one specific proprietary architecture.
But wait, if we freeze the big model to save computational costs, aren't we just shifting the bill?
How do you mean?
Well, the tiny model is brilliant, but it isn't born knowing how to write perfect diagnostic prompts. It has to learn, which requires compute. Where are the actual savings?
Ah, that is a crucial question. And it brings us to how the framework manages its resources across two phases of compute time.
Okay, so there's a strict boundary between learning and deployment.
Exactly. Let's start with phase one, training time dynamics.
Right, when the system is learning.
During phase one, the system uses reinforcement learning, specifically an algorithm called PPO, or proximal policy optimization.
Hold on, proximal policy optimization. Let's break that down for someone who doesn't spend their weekends reading machine learning papers. What is physically happening inside the computer here?
Fair enough. Think of PPO as a highly sophisticated trial and error scoring system.
Okay.
The tiny model tries writing a prompt, and the system scores how well that prompt guided the big model. Based on that score, the computer calculates mathematical gradients and performs tensor weight updates.
And tensor weight updates means it's physically rewiring the neural connections inside the AI's brain. It's changing the pathways.
Yes, this is the computationally expensive part, but here's the kicker. The target of all this computation is only the local tiny 4 billion parameter model.
So the massive 32 billion parameter giant is sitting completely idle in terms of updates.
Exactly. You're still spending compute, but you're updating a brain that is a fraction of the size. The singular goal here is to teach this tiny model how to write better prompts.
So what does this all mean for you? It means the heavy lifting of learning phase one is just teaching the little guy how to talk.
All right. And then we move to phase two, which is test time compute. Inference.
Once deployed, the rules change entirely. What happens mechanically?
Everything shifts to in-context learning and tree search. Now, there is zero gradient descent, zero tensor updates. Both models are completely frozen.
Wait, tree search, is that like the AI branching out different possible prompts in its head, simulating how the big model might react before actually sending the instruction?
That is an excellent way to describe it. The tiny model is mapping out the linguistic state space, but neither model is physically changing its internal structure anymore.
So nobody's brain is physically changing.
Not at all. The adaptation is achieved purely algorithmically through prompt activation patterns within the transformer layers.
So the adaptation is happening entirely in the conversation between them. The tiny model is just changing the specific words it uses to activate different parts of the massive model's locked brain.
Which brings us from the theory to the practice. We really need to see what this conversational adaptation looks like when things go wrong.
Let's ground this in a practical, real-world example so we can visualize it in action. Let's look at the SQL use case.
Oh, this is a great example.
So imagine you give a generic prompt, write a SQL query, and the massive model fails.
Right. If you've ever dealt with enterprise databases, you know that generic prompt sends you straight into what researchers call the failure manifold.
The failure manifold. That sounds like a sci-fi movie title.
It really just means the landscape of predictable errors. You get hallucinated columns and invalid joins because the big model lacks specific context.
And this is where the tiny model steps in, right? With the LSE intervention.
Yes, LSE stands for Linguistic State Extraction. The policy model analyzes empirical failure logs and extracts precise database quirks.
Like realizing a specific company uses weird alphanumeric strings instead of standard department IDs.
Exactly. It isolates the exact variable that caused the crash, and then it embeds that finding as a hard constraint in the next prompt.
So it tells the big model, never use standard numeric IDs and rigidly maintain this specific nomenclature.
Right. By updating this linguistic state space, the intervention mathematically restricts the output space. It physically excludes the known failure manifolds.
Oh, wow. It's like bowling with the bumpers up, but the tiny model is dynamically building and placing those bumpers based on analyzing your past gutter balls.
I love that analogy. Yes, it is scientifically accurate.
Making it mathematically impossible to throw into that specific gutter again.
Precisely. And that bumper analogy is actually a perfect bridge to the next profound scientific concept here.
Which is how these tiny text changes act as literal physical forces on the model's output.
Exactly. We call it textual perturbation. It's another concept borrowed from physics.
Okay, let's hear it. Break down perturbation for us.
In physics, perturbation theory is used to add small corrections to a Hamiltonian, a simplified model, to match reality. There's always friction, so physicists add tiny mathematical nudges to the equation.
So that's like adjusting the alignment on a car. If it pulls slightly left, you don't rebuild the entire engine block. You just apply a tiny mechanical nudge to the tie rods.
That is a brilliant translation. In the AI equivalent, the meta-model uses purely textual perturbations, words instead of mechanical adjustments.
Meaning the heuristics and constraints added to the prompt.
Right, to gently nudge the massive action model's behavior toward the target real-world environment.
Here's where it gets really interesting to me. We are bypassing millions of dollars in computing costs just by finding the perfectly worded nudge.
Yes. Crucially, generating the momentum to escape local minimums, being stuck in a mathematical rut of bad answers, doesn't require expensive tensor updates. It just requires the right words.
The power isn't in changing the brain structure. It's entirely in the rhetoric.
Exactly. Empirical heuristics iteratively align the model's behavior with reality until the error rate asymptotically approaches zero, meaning it gets functionally perfect without touching the source code.
That is just so elegant. But does this beautiful theory actually translate to better performance? Let's look at the hard data, the empirical breakthroughs.
The data is really staggering on this. The base reference they used to test this, a framework called TextGrad, sat at an accuracy of 69.1%.
Okay, which is basically a C+. Why did it get stuck there?
It struggled because it couldn't dynamically adapt to complex logical failures. It couldn't perform that deep detective work. But when they applied the LSE intervention, the AutoResearch 2.0 state-of-the-art, it jumped to 73.3%.
Wait, really? A jump of over 4% just from prompt optimization?
Yes, this is the true power of tiny models. A local 4 billion parameter Cogn model successfully diagnosed errors and steered a 7 billion parameter action model.
Boosting the architecture's performance by a massive 7% relatively. That's wild. The tiny model is rescuing a larger model.
It is. And the reason this happens is that the system defines what we call causal and topological invariance.
Basically, the underlying unchangeable laws of a specific domain.
Right. By discovering and defining those absolute architectural rules, it prevents random chaotic failures entirely.
The massive model isn't just guessing anymore. It's operating within a perfectly defined sandbox of reality.
Exactly. It's building the perfect set of bowling bumpers.
This is wild. This entire deep dive really forces us to reevaluate our approach to problem solving. I mean, if you've ever felt overwhelmed by the sheer scale of modern AI, the billions of parameters and massive server farms.
A lot, yeah.
This research proves mathematically that brute force and massive size aren't the only paths to intelligence. Efficiency and specialized architecture are just as powerful.
Absolutely. It changes how we think about scaling entirely.
So I want to leave you with a final thought to mull over as you go about your day. We've spent this time looking at how a tiny critic can fundamentally change a massive system's capabilities.
Right.
If a tiny specialized model can flawlessly steer a massive superintelligence just by changing the way it talks to it, are we moving toward a future where the most powerful entity isn't the one with the biggest brain, but simply the one who knows exactly the right questions to ask? Thank you for taking this deep dive with us today.